Welcome everybody. Today Marta is not able to chair the Encontros Scientia, so I'm here to replace and moderate. It is my pleasure to introduce and to welcome Filipe Bernardo. Filipe is from the Island Environmental Risk and Society Group in the Açores, and Filipe is also a representative of the associate members from thematic line 5 on human health. And now I will kindly ask Cristina Branquinho to introduce Filipe a little bit better, and thank you, Cristina.
Okay, good afternoon, everybody. So I'm presenting here Filipe Bernardo, which is my PhD student, together with Patricia Garcia from Azores, and also Armindo Alves from the IVAR, another research center interested on more impact of health. So Filipe is doing a very nice PhD. He's finishing formally in January and is really on a nice track. So I'm very proud of his work, and he will do a kind of a try here to present overall his PhD thesis, and I will pass the word to him, wishing him a good luck for this presentation. Thanks, Filipe.
Thank you very much. I will proceed to share the screen.
Filipe, não se está a ouvir muito bem. Tens que falar mais alto.
All right. I will just share the screen. Is it fine now? All right. So the presentation should be visible now, correct?
Yes, it's okay.
All right. Fine. Okay, thank you very much. Greetings to all the audience, both live and those who will watch the video later on YouTube. I am grateful for the invitation and opportunity to be here. And I will also like to congratulate Professor Cristina Branquinho for the recent public opening of the exhibition, Variações Naturais on the National Museum of National History. And in this presentation, since I am in the final stage of my PhD in biology by the University of the Azores, I will share the main scientific outputs of my PhD project as the due date is nearing. I want to start by providing some context and briefly stating why this PhD project was designed and what it intended or why it was needed. Here I have two excerpts in Portuguese of official documents by the Azorean government. One of them is the annual air quality report from last year, in which it's concluded that air quality is classified as good, and also from the regional legislative decree from 2012, stating that while air quality has maintained excellence in the Azores, there must be research towards finding solutions to protect and improve air quality in order to combine the development of economical activities and human activities and track the effects of climate change to continue to protect air quality. And since so far the current approach for air quality monitoring in the Azores is limited to monitoring stations with sparse distribution, with only 2 stations in the largest island, both accounting simply for background influence of urban areas, there is an opportunity here to introduce biomonitoring metrics and tools towards the interest in protecting and safeguarding air quality in the Azores. Furthermore, the environmental context is changing with increasing anthropogenic pressure. This is similar in the Azores as well as other archipelagos, other islands, which are being promoted for their touristic interests, as well as the intensification of industrial activities and urbanization to unprecedented levels. and forthcoming industries. For example, in the Azores, there is some controversy in São Miguel Island regarding the installment of an incineration central, and the impact of these future installations must also be assessed, and their assessment must be planned ahead. Furthermore, in past research published in the Azores, specifically in São Miguel Islands, there is weight of evidence concerning weight of evidence in mice and human populations. Just 2 examples. Significant histological alterations were found in the respiratory tract of mice captured in volcanic and urban areas in São Miguel Island, and also the human population chronically exposed in a volcanic area showed higher frequency of DNA damage biomarkers in the oral epithelium. And so taken together, there is a need to address this research here, which has not been done, or at least transferred or applied here. So basically, the framework of this project can be summed up as this. In the Azores Islands, and I will henceforth address specifically the island of São Miguel, which is where I conducted my project, and it is the largest island and the most inhabited. There is a particular conjugation of intensifying anthropogenic activities on a more sensitive environmental context under the confinement of an island in the ocean. But also, at the same time, there are ongoing geothermal emissions from volcanic manifestations. And what was intended originally from this PhD project was to develop a biomonitoring toolbox to address these environmental scenarios and the risks and the threats posed by these emissions, both for environmental health and public health. Therefore, the general aims of this project are based on lichens as bioindicators of air pollution, developing that biomonitoring toolbox, addressing these volcanogenic and anthropogenic threats, as I just stated, providing scientific basis and weight of evidence for promoting and guiding local policies towards the preservation of air quality. Parallelly, also to take advantage of the studies conducted on these environmental scenarios to research how lichens respond in them. And as a general outline, which this presentation will follow, there is a first section about lichens as bioindicators of anthropogenic impact by land use, and another section about lichens as bioindicators of volcanogenic emissions. So this is the first section, which resulted in 1 publication so far, with another still in the works. And this publication was recently accepted in Chemosphere. It's titled Elemental Profile of Native Lichens Display the Impact by Agriculture and Artificial Land Uses in São Miguel Island. I will start each publication by its background, by its motivation, by why each study was conducted, why it was structured, and the aims, and then of course methods and results. Islands are particularly challenged by environmental change since they are confined areas with limited availability of natural resources. Human pressure more easily surpasses sustainable limits under this confinement environment. And therefore, for example, throughout history, the extensive land use change subsequently to human settlement has brought irreversible transformation of native ecosystems, which host increasingly endangered endemic biodiversity, which showcases the ecological vulnerability inherent to smaller oceanic islands. And this happens primarily through two avenues. The first, deforestation to exploit natural resources and make way for farming and livestock, and also urbanization driven by development, human development, growing population, and more recently, touristic promotion. Therefore, monitoring the environmental impact caused by these anthropogenic activities becomes imperative, considering the special vulnerability of island ecosystems. We know that native lichens are exceptional ecological indicators which maintain equilibrium with the surrounding environment. Therefore, their elemental composition provides a time-integrated record of airborne pollutants originated by not only anthropogenic emissions, but also natural processes like volcanism. And therefore, routine and robust and adequately interpreted lichen bioaccumulation data is helpful to uncover environmental disrupting factors, which, as it is one of the objectives of this project, might be applicable by governing authorities in the implementation of corresponding corrective and mitigating measures towards environmental protection. As I stated also initially, this is something that addresses not only the Azores, but also, for instance, other Macaronesia archipelagos, which are geographically closer and share many of the same environmental challenges. So the main aims of this study were to perform a broad elemental survey of native lichens as biomonitors, naturally occurring across a primary land use gradient, encompassing forest, agricultural, and urban areas, and subsequently to determine the degree of anthropogenic disturbance, which is defined as deviation from the natural like background associated to each land use in the context of a smaller oceanic island, which is shielded and further away from major centers of air pollution, and therefore should provide a cleaner background. We wanted to understand if, predictably, agriculture and artificial areas are significantly more impacted by human activities, even though air quality is yearly reported as good, and therefore the anthropogenic impact might be somewhat overlooked. São Miguel Island is the largest and most inhabited of the Azores, with a human population of about 140,000. And in the latest land use survey, according to spot satellite orbital data, agricultural land occupies over 58% of the total area. Forest areas encompass 31%. In agricultural land, pastures are the predominant occupation, and the remaining for cultivation fields. And then artificial areas occupy a relatively small percentage of the total area, divided between urban areas, which are mostly coastal and at low altitude, and then industries and roads with 1.29%. The intensification of anthropogenic activities in recent years has been reflected in the increase of in the emissions of atmospheric pollutants since 1990. Agriculture, encompassing livestock and farming, is responsible for an increase of 83% in CO2, 93% of methane, and fossil fuel combustion for transportation and electricity contributed with 73% more CO2, 45% more methane. The agricultural land use encompasses livestock waste and the heavy application of synthetic agrochemicals, including inorganic fertilizers and pesticides, and organic agrochemicals and manure. Artificial land use includes, in São Miguel Island, vehicular traffic, thermoelectric power generation, waste management, inert extraction, transformation industries such as metalwork, woodwork, and food processing industries. The sampling design for this study was stratified by the primary land use, meaning the level 1 or the most basic land use gradients of agriculture, artificial, and forest areas, 28 suitable sites were chosen, 10 from agriculture, 10 artificial, and 8 forests. And the selection of sampling sites was mainly conditioned by altitude, which was limited to 700 meters to minimize weather variation with altitude, mainly of precipitation, which can influence the bioaccumulation levels in lichens, and land use predominance. Land use predominance was determined in a 200 meters radius buffer around each point. And for each land use, the points were selected if they had at least 50% of that land use occupation. For instance, in an agricultural site, over 50% of the total area should be occupied by agricultural terrains, and the same thing for forest and artificial sites. At mid and low elevation, the island is extensively occupied by agricultural terrains, and since the altitude is limited, this posed some sampling restrictions, because continuous forest areas are scarce at lower altitudes because of the predominance of pasture lands. And also, artificial land use occupies a very small percentage of the total area. And therefore, although we try to spatially distribute the sampling sites throughout the island, in the case of artificial sites, they had to be spatially confined to the most urbanized areas where there is greatest convergence of traffic and industries. Furthermore, the 200-meter radius buffer is the lengthiest that could be set to consistently define predominant forest or artificial sampling sites at lower altitudes. We could not use buffers lengthier than 200 meters. And furthermore, and in the case of islands, I believe this is an additional challenge in designing studies with lichens, with sampling native lichens. There, due to the confinement and space constraint, there is a lot of places that are inaccessible, and also some, if we want to find a pristine site, sometimes there are ongoing human activities nearby, and this can only be verified after on-site observation. And also, due to natural factors, phorophyte trees for sampling might be absent, or even the trees might be bare of lichens, for example, due to shielding from sunlight. And all these things can only be confirmed after on-site verification. Okay, to conduct this study from each sampling site, 5-gram sample of naturally occurring Parmotrema was collected from 3 to 5 adjacent Cryptomeria japonica trees in their trunks at 1 to 3 meters of height to avoid soil disturbance. This tree is the most widespread across the tree land uses, although it's scarce in artificial areas, but there is no other tree species that could have a similar large distribution. Native lichens were suitable to conduct this study because none of the sampling sites went through recent land use change, therefore providing temporal integration of elemental deposition. We collected large sections of the thalli from several centimeters deep from the margin to account for a significant fraction of the lichen's lifetime at each site. And although we could not use a single Parmotrema species because it was not available throughout all sampling sites, we tried to select species as close as possible, as similar as possible, and 3 species were used, Perlatum, Paticulatum, and Robustum, which are morphologically similar, with fully austin flat thalli, providing high ratio to surface area to dry weight. They are similarly tolerant to environmental disturbances like nitrogen eutrophication and sulfuric acid deposition, and they occur across the 3 land uses. And also past studies, also done in the Azores Islands, reported low interspecies variability in elemental content between Parmotrema species. Therefore, to minimize any variations between species, we chose these three, which are, at least in these aspects, very similar to each other. In each site, only the most predominant or the only species occurring was collected. The samples were collected for laboratory analysis of elemental concentrations of 58 elements and also of nitrogen. And the stable isotopic ratio of nitrogen was also determined through IRMES. And from the elemental concentrations, subsequently were calculated bioaccumulation ratios, which is the ratio of the concentration in native lichen samples against the concentration, the background concentration, which is defined according to the recent indications and the recent methodology developed by Secconi et al. 2019, are species-specific element concentrations measured in lichens, reflecting proximate natural unaltered conditions. In our study, this corresponds to the forest areas, and therefore, in order to calculate bioaccumulation ratios for artificial and agriculture areas, which are those that are under anthropogenic influence, we divided the concentrations found in these areas. We divided by the concentrations found in lichens from forest areas. And the results we obtained were as follows. Starting with nitrogen, because it was the only element in which we calculated or we analyzed concentration and isotopic ratio. Significantly higher average concentrations of nitrogen were found in agriculture and artificial land uses in comparison with forest lichens, which I will from now on consider as reference values or background values. There is a noticeable contribution of the intensive agriculture and also urban activities as source of nitrogen emissions in São Miguel Island. Although artificial and agricultural areas have similar nitrogenous contribution, their isotopic ratios are significantly different, which means that source apportionment can be done through the isotopic ratio, with agricultural lichens having a more negative signal than artificial lichens. And this, according to the literature, this corresponds mainly to ammoniacal nitrogen deposition, for which lichens have been shown to have more affinity than nitrogen oxides. There is an overall agreement between these results and past studies. For example, Pinho et al. In 2007, a similar study on mainland Portugal. Although in our study, we found even higher concentrations of nitrogen in agriculture and artificial areas. Concerning all the remaining elements, a broad elemental survey was conducted, and first of all, we analyzed through a principal component analysis the overall correlations between variables and with the land uses, and we found that almost all elements correlate positively with each other and load positively for both principal components, denoting their joint bioaccumulation, which means that where there is bioaccumulation, all elements increase their concentrations. Elements that load more positively with the first principal component have significantly greater contribution from artificial land use. And this allows the distinction of three different clusters. The first cluster are those where artificial concentrations are significantly higher than agricultural. Therefore, the first principal component denotes distinct artificial influence with an overwhelming percentage of variance over 64% and also eigenvalue of 42. And then the second cluster correlating less positively with this first principal component are those elements where artificial and agricultural concentrations do not differ significantly. And then there is a third cluster, which are the exceptions, the few elements where concentrations are higher in agricultural lichens than artificial, although only one of them, I believe mercury, was significantly higher. General elemental bioaccumulation tendencies observed. An overall pattern of significant elemental enrichment was observed in both agriculture and artificial lichens compared with the lower background values of forest lichens, including remarkably several rarer elements, which shows the remarkable sensitivity of these native lichens to elemental deposition even at very small concentrations. 57 of 59 elements except rubidium and mercury displayed higher than forest mean concentrations in both agriculture and artificial areas, and 56 of 59 elements had at least one or both significantly higher values than forest for both land uses. Furthermore, artificial lichens were more impacted by elemental bioaccumulation than agriculture, because only 9 of 59 elements have had greater mean values in agriculture than artificial. As I said, only mercury was significantly higher, and 54 of 59 elements were significantly increased in artificial land use compared with forest, while only 29 of these 59 elements were significantly increased in agricultural land use. So therefore, artificial land use through elemental bioaccumulation in lichens reflects a greater anthropogenic impact than agricultural and land use. I provide here some examples of a few elements I have chosen just to illustrate the general bioaccumulation tendencies. For the first cluster of elements where concentrations are significantly higher in native lichens from artificial areas in comparison with agriculture areas and also forest areas. For example, barium, cobalt, chromium, copper, iron, molybdenum, nickel, lead, rubidium, titanium, vanadium, and zinc. All of these elements follow this tendency and therefore were grouped in cluster 1. And here a few examples of elements from cluster 2, in which there is a similar influence of artificial and agricultural land uses. Aluminium, arsenium, cerium, cesium, hafnium, holmium, lithium, niobium, I think, selenium, uranium, and zirconium. In the end, after we obtain the elemental concentrations and knowing that forest areas provided background concentrations due to the lack of anthropogenic disturbance reflected in lower elemental concentrations, we decided to calculate bioaccumulation ratios. Following the methodology of Secconi 2019, as I mentioned before, this methodology was suggested by one of the reviewers during the peer review stage. And although the authors recommend and find this procedure can be applicable to other areas besides Italy, these cut points between levels of bioaccumulation are not validated for the Azores, only for Italy. Nevertheless, we decided to use them anyway because we do not have a similar database of over 3,000 points or values of lichen concentrations. We don't have a similar database from where to calculate these cut points. So we use these as a reference with this slight caution. We find that native lichen B ratios were generally higher in artificial than agricultural land use. Some heavy metals reach high or severe levels in artificial lichens. Some heavy metals with potential toxicity and of environmental concerns such as lead, molybdenum, manganese, vanadium, zinc, thorium, cobalt, nickel, copper, chromium, titanium, iron. And therefore, it is expressed here in a way that is easily compared or comparable with other authors and other researchers using this methodology, the distinct influences of each land use on the bioaccumulation in native lichens of a large amount of elements. Therefore, the biomonitoring approach of this study with use of native lichens uncovered the significant yet, we believe, overlooked anthropogenic impact through airborne pollution along São Miguel land use gradient. We believe that responsible authorities will look differently at this issue after noticing these results than before. Generally, agricultural land use displayed a low to moderate impact, and artificial land use displayed a moderate to high or even severe impact. Some potentially toxic heavy metals, as I just showed, reach severe levels in artificial areas. The elevated nitrogen concentrations are particularly worrisome considering the persisting issues with eutrophication of water bodies and nitrate contamination in the Azores Islands due to the intense livestock and farming. Relatively small-scale island populations can have a considerable impact over the local environment, and so ongoing biomonitoring studies and controlling measures are required toward the protection of vulnerable natural ecosystems, even if atmospheric levels are measured within legislation limits by monitoring stations. And this work provided a solid contribution of elemental bioaccumulation data across major land uses, which is valuable for compilation and comparison, for example, to establish a database of bioaccumulation data for the Azores and also other insular regions of the Macaronesia archipelagos, which face similar challenges. Now, just checking the time, entering the second part of this project, lichens as bioindicators of volcanic hydrothermal emissions. Two publications resulted from this component. The first one is thalospatial modeling the risk areas of chronic exposure to hydrothermal volcanic emissions using lichens. Human populations and volcanic areas are increasingly overlapping, and 10% of the human population is affected by volcanic activity, whether through devastating eruption episodes or chronic exposure to volcanogenic air pollution. Volcanic emissions contain hazardous gases and aerosols and particles for humans, which can carry potential adverse health effects, particularly cardiorespiratory conditions due to acute overexposure or, more concerningly, repeated or chronic exposure to lower concentrations of airborne pollutants. The main route of exposure is the inhalation of the air mixture in outdoors conditions. Therefore, it is realistically challenging to assess the chronic exposure, accounting for this dilution factor, the dispersal to invariable weather conditions, and also monitoring stations lacking often spatial representativity and resolution, for which costly and impractical use of equipment is required. Lichens provide the solution for this, reflecting the time-integrated wet and dry deposition of air pollutants, allowing cost-effective tools for mapping spatial and temporal patterns of air pollution. Therefore, the main aims of this study were using lichens as biomonitors to spatially trace with time integration airborne hydrothermal emissions in outdoor conditions and develop a methodology to spatially model with high resolution the risk areas of human chronic exposure by combining lichen biomonitoring data with human population data. The study area is furnace, an hydrothermal volcanically active environment encompassing fumarolic fields, thermal and cold CO2 springs, and soil diffused degassing. There is almost 1,000 daily tons of hydrothermal CO2 released, and also H2S, radon, and other gases and associated particulate matter. The population living in Furnas village is chronically exposed to volcanogenic emissions. 58% of the houses are built on top of hydrothermal CO2 emanations. There are 1,500 inhabitants plus tourists. And there is also occupational exposure to decaying farming soils. And previous studies done in the population of that village established ways of evidence concerning adverse health effects related to the chronic exposure to this volcanic environment. Lung injury and testicular injury in studies with wild mice, and also higher risk of cancer development or respiratory tract and breast, DNA damage, chromosome damage on oral epithelia, and restrictive defects and COPD syndrome. To conduct this study, lichens were collected from a reference site, a forest reserve outside volcano caldera, and transplanted to the study area, while reference samples were auto-transplanted and kept on the reference site to account for the experimental handling of the transplant, just the act of removing the lichen from the tree and putting on the transplant bag, and also to obtain background values away from the volcanic area. And then an exposure period of 6 months followed, after which both reference samples and transplants were retrieved for analysis. These transplants were placed at 1.5 meters from the ground in free airflow nets, which is approximately human respiratory height. Transplanted lichens were more suitable in this case over native lichens because they allow flexibility in spatial distribution, a well-defined exposure period, and also they ensure exposure-free condition at the beginning before being exposed to the volcanic area. The species used near Rubicunda was selected because it naturally occurs in the volcanic area, displaying a degree of tolerance to volcanic pollution to survive the experiment, and also because its shrubby fruticose enhances particle interception. Transplants were distributed according to the gradient of soil CO2 flux reported by Viveiros et al. 2010 for Furnas caldera, with stratification by potential exposure to hydrothermal emissions, and to cover homogeneously the study area. About a balanced number of 3 transplants was distributed within each of the 10 classes of the soil CO2 flux gradient, with the highest classes sampled more densely with 6-7 transplants. After exposure, the lichen samples were collected. In situ, soil CO2 flux was measured below each transplant, and also the lichen samples were analyzed for elemental concentrations and isotopic analysis of sulfur, which then was used for spatially modeling of the hydrothermal emissions, and then afterwards mapping risk areas of chronic exposure. Measuring the soil CO2 flux at soil level below each transplant was a poor predictor of exposure to hydrothermal degassing because soil properties, namely soil permeability, affect the release of the hydrothermal emissions to the air. We can have, for instance, a fumarolic field releasing a large amount of hydrothermal emissions in a given point. However, in specific site where the transplant bag is placed, the soil might have low permeability, and therefore this did not correlate well with the initial gradient that was used to distribute the sample. From the analyzed elements and variables on the lichen samples, the isotopic signature of sulfur, delta 34S, showed to be a promising tracer of airborne hydrothermal emissions in outdoor conditions, since it correlates very closely with the distance to the fumarolic fields. where there is emanation of H2S. As it can be seen here, they are quite close in the principal component analysis, and using a regression model on a logarithmic function, this relationship between the isotopic ratio of sulfur and distance is established with a high squared R, and the isotopic signature of sulfur tends to decrease towards 0 or negative values with the distance gradient, denoting the influence of the fumarolic source. As the distance decreases to the fumarolic fields, the values also decrease of the isotopic signature. The percentage in terms of concentration of sulfur was not as consistent as the isotopic signature, and the isotopic signature also is not correlated with the bioaccumulated sulfur. Therefore, the isotopic signature is a more suitable tracer than the concentrations themselves, because it deals with the abundance, the relative abundance of isotopes rather than the concentration of the elements. The spatial modeling of the delta 34S shows fumarolic fields as distinctly major sources of airborne volcanogenic sulfur in Furnas volcano, as it can be seen in this interpolation map, where the values of delta 34S decrease with the proximity to the fumarolic fields. Therefore, this allowed the spatial mapping and the construction of exposure risk map according to the following methodology. Here is an area view of the study area, encompassing or including the area where the samples were placed, the transplants. Then we have here the habitational areas of Furnas village. And then by conjugating with the interpolation map of the delta 34S isotopic signature, an intersection was made between both layers, creating a 900 square meter grid, which is the resolution of the resulting risk map. Each unit, each cell is 30 by 30 meters. And then the risk level was calculated according with a classic formula of hazard and exposure, where, since habitational areas were used as a proxy of ongoing human presence, the risk is low where the isotopic signature of sulfur is high or has high values, and habitational areas have low percentage, meaning less ongoing human presence. And then the risk increases to high, being maximum risk, where habitational areas are close to 100%, and also the values of delta 34S are more negative, denoting the presence of hydrothermal emissions and hydrothermal air pollution. As these individual cells were then separated by the individual values of the two components of the risk formula, pairing them both provided then a final map which categorizes the habitational areas according to the risk level, and we determined that almost 26% of Furnas village habitational areas, mostly around the Furnas fumarolic fields, are at high or very high risk of chronic exposure to volcanogenic air pollution as traced by the sulfur isotopic signature. And we therefore established a model which can be adapted to other volcanic areas in the world, inclusively, and other proxies of human exposure can be used instead of habitational areas, which is an indirect measure, in which the fumarolic influence is given by distance to fumarolic fields and delta 34S, and then the exposure risk level pairs habitational area or another proxy of human exposure and the isotopic signature of sulfur. Therefore, isotopic signature software is a time-integrated tracer of airborne hydrothermal emissions. The model assessed chronic exposure to volcanic air pollution in outdoor conditions. Habitational risk areas are shown in a high spatial resolution map with time integration. This methodology is replicable in other volcanic areas, and resulting maps are useful for correlating exposure data with population health outcomes, spatially focusing future research, future assessments, and upholding health safety measures in volcanic areas. Finally, the third publication, also relating to lichens as indicators of volcanogenic pollution, talus structural alterations in green algal lichens. I will try to do this as quick as possible within time. As indicators, talus structural alterations in green algal lichens as indicators of elevated CO2 in a degassing volcanic area. This study followed the same experimental design of the previous study. The same lichen transplants were used, not the same number, but it was the same procedure, the same transplant, and the same exposure time of 6 months in the same study area, Furnace Village, and also including the same reference sites. The motivation for this study pertains to the relevance of volcanic areas for the release of CO2 to the atmosphere, providing natural laboratories where we can study how organisms deal with the abundance of CO2 in natural conditions. It remains of interest to know if lichens and cryptogamic covers are benefits of a productivity increase due to the increase of CO2 levels worldwide. And lichens are more suitable than plants to evaluate the effects of rising CO2 concentrations because they are poikilioid organisms and they depend more exclusively on the air for mineral and water nutrition, and therefore they more closely resemble the concentrations or the composition of the air. Also, the studies performed about how lichens deal with elevated CO2 in natural conditions are few so far and have not clearly demonstrated benefits to lichen productivity. Therefore, in this study, we propose to track the structural response of a green algal lichen, which is the same species used in Rubicunda, which is green algal lichens are known to be sensitive to variations in external CO2 concentrations following the transplantation and exposure to the volcanic degassing area under non-limiting temperate oceanic climate of mild temperatures and constantly high air humidity, which means that the transplants will have will be photosynthetically active throughout most of the time, and therefore we can measure if there is a productivity increase, even if by indirect means, such as histomorphometric approaches, which are tested in this experiment to see if they are suitable response biomarkers to determine what is the outcome or the response of lichens and how the symbionts interact with each other. The study area is the same, Furnace Village, just noting that anthropogenic activities are low in this village, therefore the CO2 is almost all of volcanogenic origin, except that which is of biogenic origin. Same as experimental design, I will skip this because the time is getting short. And also just highlight here that both reference site and the study area at Furnace Village have same macroclimatic conditions. Therefore, these are non-limiting for the response of lichens in either area. The reference samples were left at reference site away from the hydrothermal CO2. The same kind of transplant bag was used. By using lichen transplants, it was more suitable to ensure totally free, exposure-free condition before or during the time of the experiment, encompassing, meaning that the lichens were not exposed to higher CO2 concentrations than at any point of their lifetime. After 6 months, the samples were retrieved and the nitrogen content was measured. I can say in advance that there were no differences in the nitrogen content between reference samples and transplanted samples, which means that reference samples were not limited by lack of nitrogen in their productivity. After retrieval, the samples were subjected to a customized protocol of histological processing. We gathered replicate marginal tips, 1 centimeter tips from healthy tally of each transplant. This is because these are the youngest portions of the tally and also the most metabolically active, and therefore the section of the tally with greatest overlapping with the exposure period during the experiments with high CO2 concentrations in the air. The histological processing was done from fixation to staining and obtaining histological slides observed at light microscopy. And after obtaining these histological slides, some histomorphometric measurements were made, namely the relative volumetric density of each of the 3 tallene layers of Eugenia rubicunda, namely the cortex, the medulla, cortex here, medulla here, and then the central port, and also algal cells. A separate algal layer was not considered because, at least in this species, algal cells tend to occur aggregated in pockets. Therefore, another approach was followed to measure the percentage of algal occupation, not by thickness, but by superimposing a rectangular area over the outermost section of the histological slide, and then measuring the area occupied by algal cells or by algal pockets in the lichen tally. Therefore, two measures of the tallene layers were obtained: the relative volumetric density, which is a relative measure, and the thicknesses, which are an absolute measure, and then the relative percentage of algal occupation. And the results show that samples from furnace are overall thicker, mostly due to significantly increased thicknesses of medulla and central port. The relative volumetric density of cortex and medulla decreased, while reversely it significantly increased for the central port. This indicates that the symbiotic partnership in furnace transplants produced significantly more biomass than reference lichens, and this biomass was predominantly allocated to the fungal hyphal tissue in the central port. Therefore, there was noticeably a thickening of the central port. The symbiotic partnership benefited of a productivity boost after exposure at the volcanic degassing area. There is an increase of 14.8% in the thickness of the central port and 8% of the combination of cortex and medulla, which are the central port is the more structural layer, and the cortex and the medulla are the more physiological, if we want, layers. And then in combination, in conjugation, in total thickness, there is an increase of 12.5%. The percentage of algal occupation is significantly higher in reference samples than furnace transplants. And this indicates that there was a greater efficiency of algal cells in fueling biomass productivity in furnace transplants while exposed to airborne degassing CO2 over the time of the experiment. In turn, reference samples were unable to produce as much fungal biomass over the same exposure period, despite having more percentage of algal occupation. Therefore, there is here a productivity boost, which is attributable to the greater availability of airborne CO2 for the photobiomes. This effect was relevant at the level of the whole furnace caldera without any discernible gradient, like the distance gradient to fumarolic fields in the case of the isotopic ratio of sulfur, and which matches the spatially diffuse nature of soil degassing emissions of CO2. which means CO2 levels should be increased relatively evenly in the air at furnace caldera at transplant height, and therefore furnace transplants enjoyed a more enriched air mixture than reference samples over the time of the experiment, which explains the observed structural alterations. In conclusion, the histomorphometric approach showed that Ujner ruby couldn't undergo significant structural alterations as a primary response to transplantation to an actively degassing volcanic environment. The greater availability of airborne CO2 under non-limiting climatic conditions in the hydrothermal area promoted a beneficial response in terms of lichen biomass productivity, as I already explained. Algal cells showed greater capacity to sustain additional fungal biomass production and driving lichen growth at ambient conditions with the enrichment of CO2 in the atmosphere. And this histomorphometric approach and the parameters that were measured are time-integrated response biomarkers. In the case of atromurus, which means with separate layers, tallene layers, and these green algal lichens with potential application in related research, elucidating how lichens adapt to changes over time, such as the globally rising CO2 levels in the environment. And I have finished. I have now just make I want to give my acknowledgements to the co-authors and the team, namely Pedro Pinho, Paula March, Professor Cristina Branquinho, Professor Fátima Viveres, and Professor Armindo Rodrigues, my co-supervisor also from the IVAR, Pedro, Paula, and Professor Cristina from the E-Changes of C3C, and also, of course, my supervisor, Patricia Garcia, and also an undergraduate student, Tanya Rocha, in biology, which helped me with the third study about the hydrothermal CO2 effect on lichen productivity. And of course, I thank Fundo Regional para a Ciência e Tecnologia and the funds from Programa Operacional FSS 2020 of the Azorean government and the collaboration of IVAR. Thank you very much.
Thank you, Filipe. Thank you very much for this really nice presentation, this very important work. And also it's very nice to see that this is a collaboration between and a co-orientation between two groups in the C3C, which is always nice. Thank you very much. So I think we have here a comment on Artur Gil. So in the first place, Artur congratulates you for your very excellent work. And he has a question. I will then translate. Okay, so Artur asks, how cost effective in terms of financial costs especially would be the implementation of a long-term lichen-based operational monitoring system in an island such as São Miguel? And at the end, is that significantly cheaper or more expensive than standard monitoring methods or instruments? Can you answer?
I think that it can be surprisingly cost-effective, especially, of course, if the sampling design is well done, and especially also with the involvement of people who perform this kind of research for many years. The sampling design can be done in ways that can be very cost-effective. And not only that, I think the advantage is not only about cost effectiveness, but also the kind of information that it provides that's not possible to obtain through conventional monitoring regarding effects of ecosystems and living organisms, which I believe is an even greater advantage of lichen biomonitoring. And I think that at least for a start, or at least to convince local authorities to invest in this research, some biomonitoring studies can be done with relatively low investment, which is mostly allocated to the chemical analysis, basically.
Mm-hmm. Thank you, Filipe. So otherwise, we have some comments congratulating you, Helena Serrano, Patrícia Garcia Pereira, Marta Santos, Lourdes Silva. I think there are no more questions, so I would ask one very briefly myself. So when do you think that you can really impact on the governance? So have you tried to really put this to work and present it to the people that can put this in place?
In the beginning of the project, there was some companies of the Azores. They manifested interest in the project, although not supporting financially, but manifested interest. And now that we have the results, now that we have some work done, the next step immediately after the PhD is to take these results to them and show them the potential of this research. And also, specifically in the case of the first publication, the concerning evidence that the activities carried need a closer look needs to be taken at the activities, agricultural and urban activities that are currently intensifying in the Azores. And I believe that after seeing that data, there will be increased interest by these, not only by the government, but also by the environmental departments of the entities involved in these activities.
It's quite complicated, though, to try to reallocate populations that live near the volcanoes, right? It must be complicated, I guess.
Yes, this is traditionally an issue because there is a lot of research showing that those are risk areas for human population. But it's very hard for families that are living there for many generations to live there. And especially in islands, it's a different context because even a single village can feel like a district. So for those that are born there and live there for a long time, it's not easy. Although there are protective measures that can be done. For example, in the case of indoors, radon and CO2, and CO2 emissions indoors, which can happen through the subsoil of the house. There are some recommendations to the population to ventilate the houses so that there is an accumulation of gases inside the house. And this effort has been done.
Okay, and do you think that the populations would hear with goodwill from a scientist just explaining them exactly this? Yes? Oh, that's good.
It's in their interest for their own health, and also even as I was carrying out this study at Furnace, I saw also, because I had to ask for the consent of a few villagers to place the lichen transplant bags in a few properties, to protect from random thefts, and some of them were actually interested in hearing back from the results of the study.
Nice.
So I believe that they will be receptive to that.
That is really nice. Thank you. I would ask very briefly, Christina, if you want to comment or ask something. I mean, ask, I don't believe, but
just to congratulate also Filipe for his talk and for the work he's been doing on the right time. So he's been completely fulfilling the time, which is always very good for a PhD student. So he just needs to write the discussion, and that's it. So, and I would like just to add what he said. So, although it's difficult to change people from villages, at least at the municipal direct program, you can establish which areas will not be anymore for living, and you also can help people which are living there and don't want to change to have some measures such as the ones that Filipe said, to improve their health, and you can help them to do that using better windows, the circulation, making the right circulation, and educating them in relation to that, because that can decrease a lot the exposure to those problems. So I think it's always important, the knowledge is always important, so that we can really focus our attention on the right places.
Yeah, exactly. So Okay, thank you very much, Cristina. Thank you very much, Filipe. I believe that there are no more questions, only some congratulations. And I would I would like to finish and wrap up, of course, in the first place. So thanking very much, Filipe, for being here and presenting this very nice and interesting and important work. And wishing him the best for the rest of the PhD.
Thank you very much.
Until you're going to finish briefly, I understand. And also I would also want to thank Cristina Branquinho for being here and also presenting a little bit better Filipe. I would also very importantly thank Mariana Marques for being in the backstage and making this possible with all the logistics that is behind this. And finally, I would also like to thank Marta Santos, because although she's not here, she prepared everything in advance so that we could have this one more Encontros Scientia. Okay, so thank you all. Thank you everybody to be here and to listen and to participate. And I wish you a nice week and hope to see you next week back here in a week. Okay, so bye-bye and thank you all for being here.
Goodbye and thank you.
Goodbye. Thank you.
Depois falamos melhor, está bem? Beijinhos, adeus, Gabriela.
Adeus.